Hey guys, I am going to give the solution of assignment 7. So in this assignment 7, we will solve the integration by using the complex value integration and such type of integral is known as type 2 integral. So now here the type 2 integral will be in the form of the integral I, that is negative infinity to infinity f1x upon f2x dx. So such type of integral is known as improper integral. Improper integral. So now this integral will be solved by using the complex integral over the curve C f of z dz. So what is the properties? What will be the properties of the integral that is the one? Let us suppose that is the one. So our its first property, that is first property will be f1 and f2 are are polynomials with degree of f1 is equal to m and degree of f2 is equal to n. And now the second property, that is degree of f2 always greater than the degree of f1 plus 2. That means we can say in word degree of f2 should have at least 2. At least 2. So that is a very important, at least 2. At least 2 as compared to the function f1. And the third property is that f2 has a simple simple zeros at the x1, x2, x3, but we know that degree of f2, that is n, so zeros will be n, xn on the all the zero which lies on the x-axis. So these are the first three property of the given improper integral. So first property, that is f1 f2 is a polynomial, degree of f1 that is m, or degree of f2 that is n. And second property, degree of f2 should be at least 2, so we can write degree of f2 greater than equal to degree of f1 plus 2. So in terms of mathematical notation, we can write n should be greater than equal to m plus 2. So that is the important. Mean degree of f2 should have at least degree 2 as compared to f1. And the third property is that f2 has a simple zeros at x1, x2, x3 up to xn, because degree of f2 that is n. So number of zeros will be n, which will lie on the real x axis. Now now further we will discuss how can we solve this type of integral in terms of complex integration. What we'll do? So first of all, I am going to give you algorithm. So in this algorithm, first of all, you need to assume the given integral I, which define negative infinity to positive infinity f1 of x upon f2 of x dx. So here we need to assume, or we can assume, let f of x is equal to f1x and upon f2x. So now second, we need to replace x by z. Then this integral will convert into the complex integral over the c. This whole function will change into f of z dz, where the curve c we can write that is a curve, that is a curve, sorry, that is a curve of upper half circle C having a radius r of, that is a large circle having a center that is 0, that is we can write mod of z is equal to r, and real axis which vary from negative r to positive r. So let us draw the diagram. So first of all, we need to draw the y-axis, that is a y-axis, that is a x-axis, that is a x dash x, and that is a y and y dash, and the radius vary from, because that is upper half circle, so it is a very big, so we will the radius value will vary from negative r to r. We need to keep the center as a 0. We have to make the semi upper half circle here, so that will be the center 0, and the direction is anti-clockwise. In other words, we can say the counterclockwise. That is a, we can say in terms of, that is a real axis, and that this curve will be known as the circle having a radius r. So further, so we will consider this region. This region is a region of integration. That will be our region of integration, that we can say that is a capital D. That is a capital D domain of integration, or we can say over the curve C. So now, this whole complex integration over the curve C, f of z dz, is the sum of the line integral which vary from negative r to r f of x dx plus the line integral over the curve C of radius r f of z dz. So we need to find, so this will be solved by using residue theorem, and this integral will be solved by using ML inequality and further we will, after solving, we will apply the limit, that is r tending to infinity, on both sides. Then we will get, after taking the infinity, that is the limit r tending to infinity over the curve C f of z dz is equal to the limit r tending to infinity negative r to r f of x dx plus, that is the limit r tending to infinity over the curve C having a radius r f of z dz. So now we need to simplify. So in this integral, we will substitute the value of z as r e to the power of I theta. So now as r tending to infinity, after simplifying r tending to infinity, the value of the integral over the r f of z dz will be give to 0. And 0, when this integral will be 0, so now this integral will convert, because after taking the infinity r tending to infinity, we will solve by using the summation of, that is I is equal to 1 to n, the residue theorem at z is equal to zi, and this will be equal to, when I will take the r tending to infinity, this integral will change into negative infinity to infinity f of x dx. So in last we will say this value will be required solution of this given integral. So finally we can say that the value of the integral negative infinity to infinity f of x dx will be equal to 2 pi I summation vary from I is equal to 1 to n residue at z is equal to zi, and this is our required final answer. So by using this concept, we will solve the following problem. So let us consider the first problem. So in the first problem, as we can see that, first of all, we need to take the integral I, that is given 0 to infinity dx upon 1 plus x squared to the whole power 3. But as we can see that this integral is not in the form of negative infinity to infinity. So first of all, we need to convert this integral into negative infinity to infinity f of x dx. So now here, what is the basic concept here? So we will write here in the right hand side. So here the f of x is equal to 1 upon 1 plus x squared to the whole power 3. And further, as you can see, If I replace the negative x, so what will be here? That is 1 plus negative x whole square to the whole power 3. So this will be equal to 1 plus x square to the whole power 3. So that is equal to f of x. It implies f of negative x is equal to f of x. That it is a even function. And as we know that, so what is the property here? We will use f negative a to a f of x dx is equal to 2 times of 0 to a f of x dx if the function f is even function. So we can write here this integral 0 to a f of x dx 1 by 2 times of negative a to a f of x dx. So we need to replace a by infinity. Then, so we can write this integral 0 to infinity f of x dx 1 by 2 times negative infinity to infinity f of x dx. So this is our required basic concept of this integral. So by using that, so so now we will start the solution from here. So now I am going to give the solution from here. So now let us consider the given integral I, that 0 to infinity dx upon 1 plus x square to the whole power 3. So this can be written as, by using the above concept, 1 by 2 times negative infinity to infinity dx upon 1 plus x square to the whole power 3. So now we need to replace. Now this is our integral 1. Further we need to replace x by z. Then the integral I will be 1 by 2 times, and this negative infinity to infinity will change into the Cauchy, that is dz over 1 plus z square to the whole power 3, where the Cauchy, that is mod of z, is equal to r. So now here we will draw the diagram here, that is upper half circle, center that is a 0, so that is a r, that is a negative r. So direction will be the counterclockwise, that will C having the curve having radius r. This is our domain of integration, and we can say that this r is very large. So now further, the integral 1 over 2 over the curve C dz over 1 plus z square will be equal to the sum of the integral negative r to r f of x dx plus over the curve C of r, that is f of z dz. So that is our equation number 2. So now, first of all, we need to solve this integral. So let consider the capital I1, that is a 1 by 2 over the curve C dz upon 1 plus z square to the whole power 3. So now first of all we need to find the singularity. So we need to put 1 plus z square is equal to 0 to the whole power 3 is equal to 0. It will show the value of z is equal to plus minus I how many times? 3 times. So we can say the singular points are z is equal to plus minus I, but only z is equal to I lie in the upper half circle, only I. So therefore we can say that z is equal to I, mean that will be, so that is here z is equal to I lies in the domain D. So we can say z is equal to I is a pole of order 3, will pole of order 3. If pole of order 3, then the value of integral over the curve C dz upon 1 plus z square to the whole power 3 is equal to 2 pi I residue at z is equal to I, and this is calculated by using Cauchy residue theorem. So further we will solve, that is 2 pi I, and this residue formula for the residue for the order 3 will be limit z tending to I 1 upon 3 negative 1 factorial, that is d2 over dz square z negative I to the whole power 3 f of z, that is 1 upon 1 plus z square to the whole power 3. So now further simplifying, this value is equal to 2 pi I upon 2 factorial limit z tending to I d2 over dz square, that is z negative I to the whole power 3 multiplied to 1 upon z plus I to the whole power 3 z negative I to the whole power 3. You can see this factor get cancelled out. So now further this value is equal to, that is 2 to get, also here 2 to get cancelled out. So we will get, that is a pi I multiplied to limit z tending to I d2 over dz square 1 upon z plus I to the whole power 3. So now further this can be written as pi I limit z tending to I second derivative of z square z plus I to the whole power 3, that is a negative 3. So here will, there is a pi I multiplied to the limit z tending to I second derivative, that is a negative 3, that is a negative 4, and here will be z negative z plus I to the whole power negative 5. So it will give 12 times of pi I. Apply the limit that is 1 plus I to the whole power negative 5. It will give 12 pi I over 2I to the whole power 5. So further simplifying, this value is equal to 12 pi I, 12 to the power 5. It will give 32 times of I. You can see that I to I get cancelled out, and that is 4 3 is a 12, and here will be that is 4 8 is a 32, and this value is equal to that is 3 pi over 8. So now here in the whole term, because that is here 2, so we have to divide the whole term by 2. So that will be divided by 2. It will give pi I by 2, and further will be that is a pi I divided by 2, pi I divided by 2, and divided by 2, divided by 2, divided by 2, divided by 2, and it will give divided by 2, that is 3 pi over 16. So we can say the value of the integral 1 by 2 over the curve C dz over 1 plus z square to the whole power 3 is equal to 3 pi over 16. Now we need to calculate. Now to find the integral over the curve C of R f of z dz, where f of z is equal to 1 by 2 1 plus z square to the whole power 3. So now first of all, over the circle having a radius r, we will put the substitution. We need to put z is equal to r e to the power of I theta on a value of z is dz, that is r I e to the power of I theta d theta, and this value is equal to r I z d theta. So we can write here that is d theta is equal to dz, sorry, we will write here dz is equal to r I e to the power of I theta d theta, and after taking the mod on both sides, it will give that is r, and mod of dz will be equal to r d theta. So this is here our required value. So this is our required value, and also we know that the mod of z1 plus z2 is greater than equal to mod of z1 negative mod of z2. So now by using the mod of z square plus 1 is greater than equal to mod of z square whole square negative mod of 1 square. So we can write that is a mod of z mod of z, sorry, mod of z square, mod of z square negative mod of 1. So we can write mod of z whole square negative 1, that is r square negative 1. So by taking the reciprocal, 1 upon mod of z square plus 1 will be less than equal to 1 upon r square negative 1. So finally, by using ML inequality, by using ML inequality, take the mod over the curve C of R f of z dz. So this will be equal to line integral over the curve C of R mod of f of z dz, and this can be solved at this is less than equal to over the curve C of R mod of f of z mod of dz. So now here mod of f of z is equal to the mod of 1 upon 2 times of mod multiplied to z square plus 1 to the whole power 3. So by using this concept, we write here that is less than equal to 1 upon 2 times of r square negative 1 to the whole power 3. So after the substitution, as we can see the circle upper half plane, this half circle theta vary from that is 0 to pi. So this integral will change into 0 to pi 1 upon 2 times of r square negative 1 to the whole power 3 value of dz, that is r d theta. So that is a function of r. Take outsides 2 times of r square negative whole power 3 multiply to 0 to pi d theta, and value of this integral will be that is r times of pi over 2 times of r square negative 1 to the whole power 3. And as so we can say that the magnitude of the line integral over the curve C with having radius r mod of f of z dz is less than equal to r pi over 2 r square negative 1 to the whole power 3. So as r tending to infinity, the rational function r pi over 2 times of r square negative 1 to the whole power 3 will give to 0. If this modulus value becomes 0, so we can say the limit r tending to infinity over the curve C of r f of z dz has to be 0. So this is a very important concept. So further, the value of the line integral over the curve C f of z dz is equal to integral vary from negative r to r f of x dx plus over the curve C of r f of z dz. So now as r tending to infinity, the limit r tending to infinity over the curve C f of z dz, this limit will be that is a negative infinity to infinity f of x dx plus apply the limit here r tending to infinity over the curve C with respect to r f of z dz. So further we can find here this value will be by residue theorem 3 pi over 16, and that, so this can be written as 2 times of, sorry, so now this will be equal to 1 by 2 integral negative infinity to infinity f of, sorry, dx over 1 plus x square to the whole power 3, that will be 0. So now here that is 2 and the 2, 2 8 is 16, so it will give 3 pi over 8, that is negative infinity to infinity f of x 1 plus x square. It implies 3 pi over 8 will be equal to the 2 times of 0 to infinity dx over 1 plus x square to the whole power 3. So therefore the value of integral 0 to infinity dx over 1 plus x square to the whole power 3 is equal to 3 pi over 16, and this is our required final answer. So now in this integral, so first of all, so let us consider the given integral negative infinity to infinity x square dx upon 1 plus x square, the 4 plus x square. So in this integral we need to replace x by z, then the integral will be changed into, that is a complex integration over the c z square dz over 1 plus z square 4 plus z square, and the where the curve C is a circle centered at 0 having a radius r. So we can draw the diagram, or we can draw the curve. So this curve will be, so that is, it's vary from negative r to r, and that is the upper half circle with having a center 0, and this curve, that is a curve C over the radius r, and the direction will be counterclockwise as anti-clockwise. So now further the integral over the curve C f of z dz, this whole integral will sum of the integral over the real axis negative r to r f of x dx plus the line integral over the curve C having a radius r f of z dz. So let us suppose this integral will be, that is a 1. So now here first of all we'll find the value of integral f of z dz is equal to line integral over the curve C z square dz over 1 plus z square and 4 plus z square. So this can be calculated as 2 pi I, the sum of residue vary from 1 to n, that is residue, sum of the residue at z is equal to zi. That is equation number 2. The first of all we need to find the singularity, that is substitute 1 plus z square multiplied to 4 plus z square is equal to 0. So from here value of z is equal to plus minus I and plus minus 2 times of I. So you can see only z is equal to I and 2I belongs to the upper half circle, that is mod of z is equal to r, and we already know that this radius r is, it is a very large value. So we can say that z is equal to I and z is equal to 2I are both are simple pole. If these are simple pole, then by equation 2 the sum of the residue which vary from I is equal to 1 to 2 residue at z is equal to zi, that is residue at z is equal to z1 plus residue at z is equal to z2. The first z1, that is z is equal to I, second that is residue z is equal to 2I. As we know these are both are simple poles, so we can calculate at this value is equal to the limit z tending to I, z negative I, z square over 1 plus z square and 4 plus z square plus limit z tending to 2I, that is z negative 2I multiplied to z square over 1 plus z square multiplied to 4 plus z square. So further simplifying we will get, that is the limit z tending to I, that is z. So you can see this factor will be cancelled out, that is a 1 z negative I, z plus I, that is 4 plus z square. So now here will be the limit z tending to 2 times of I, z negative 2I, z square over 1 plus z square, z negative 2I and z plus 2I. So you can see this factor will be cancelled out, this factor will be cancelled out. So now further this value is equal to the limit. So now we can put the limit here, that is I square over I plus I, that is 2 times of I multiply to 4 negative 1 I square, that is negative 1 plus 2I2 whole square over 1 plus 2I2 whole square, and that is 2I plus 2I, that is a 4I, that is a 4I. So now further this value is equal to, that is a negative 1 upon, that is a 6I, 3 to the 6I, that is a negative 4 over, that is a 1 negative 4 multiplied to 4I. So this will give negative 1 upon 6I, and it will give 4. You can see that is a 4 get cancel out, so it will give that is 1 upon 3i. So now further simplifying, this value is equal to, that is I by 6 negative I by 3. So this value is equal to negative I by 6. So therefore, so we can say that the value of the integral over the curve C z square dz over 1 plus z square multiplied to 4 negative z square is equal to 2 pi I multiplied to the sum of residue, its value, that is negative I by 6. So it will give, that is 2 and 2, 2 3 the 6. So it will give, that is a pi over 3. So now further equation 1 will be the value of the integral negative r to r f of x dx plus over the curve C having a radius r f of z dz is equal to pi over 3. So now we need to calculate the value of this integral. So now for the integral over the curve C of r, C over the r f of z dz, so we need to put value of z, that is r e to the power of I theta. So now here dz is equal to r I e to the power of I theta d theta. So now mod of z is equal to r and mod of dz is equal to r d theta. So this is a required value. And further, so now take the modulus over the curve C, because we need to make this integral as a real value integral, so we need to take the modulus f of z dz. So by using the ML inequality, it will give the integration over the curve C, that is the mod of f of z dz. So this will equal to less than equal to over the curve C of r mod of f of z dz, mod of dz. So now here, but as we know that mod of 1 plus z square and z square plus 4 will be greater than equal to mod of z square negative 1 and product of mod of z square negative 4. So this value is equal to r square negative 1 and r square negative 4. So we can say that 1 upon mod of 1 plus z square multiplied to 4 plus z square less than equal to 1 upon r square negative 1 and r square negative 4. So now here this is equal to the line integral over the curve C mod of z square over mod of z square plus 1 and mod of z square plus 4 and mod of dz. So this value after putting the polar form, so the angle vary from 0 to pi, and that is r square over r square negative 1 r square negative 4 r d theta. So further simplifying, so this is the whole term from here, that is a function of r. So take outside, that is r to the power 3 over r square negative 1, that is r square negative 4 0 to pi d theta, and this value is equal to value of this integral will equal to, that is a pi. So put this value here, that is r to the power of 3 pi over r square negative 1 and r square negative 4. So now further we can take the limit. So we can write here as the capital R tending to infinity, the rational function r cube pi over r square negative 1 multiplied to r square negative 4 tending to 0. So we can say that the limit, sorry, the value of line integral over the curve C r f of z dz will tend to 0 as r tending to infinity. So now apply the limit on both sides, the limit r tending to infinity negative r to r f of x dx plus the limit r tending to infinity over the curve C of r f of z dz is equal to pi by 6. So now here this value, it implies negative infinity to positive infinity f of x dx, and this value will be that is 0 is equal to pi by 6. So therefore finally we can write the value of this integral negative infinity to positive infinity x square dx over 1 plus x square and 4 plus x square is equal to pi over 6, and this is our required final answer. In the problem third, in the problem third, so let us consider the given integral I, that is 0 to infinity cos of 3x dx over 1 plus x square multiplied to 4 plus x square. So as we can see that the function f of x, that is cos of 3x over 1 plus x square and 4 plus x square, it satisfies this condition f of negative x is equal to f of x. It implies given function f is even function. So the even function can be written as, so that this integral can be written as 0 to infinity cos of 3x dx over 1 plus x square multiplied to 4 plus x square is equal to 1 by 2 times negative infinity to infinity cos of 3x dx over 1 plus x square and 4 plus x square. And now we need to replace x by z. Then half of integral negative infinity to infinity cos of 3x dx over 1 plus x square multiplied to 4 plus x square is equal to 1 by 2 over the curve C cos of 3 times of z dz over 1 plus z square and 4 plus z square. So as we can see that we can draw the curve C as, so let us draw, this is our x axis and this is our y axis. So the curve along the x axis, it will vary from negative r to the positive r, and here will this is a half circle, so this red center will be, that is 0, and uh, and the direction will be counterclockwise, and this curve will be c along the r. So this integral will be the sum of the curve along the x-axis and along the curve C having a radius r. So we can write from the given diagram half of the over the curve C, that is mod of z is equal to r cos of 3z dz over 1 plus z square 4 plus z square is equal to the value of the integral vary from 1 by 2, that is negative r to r f of x dx plus half of over the curve C having a radius r f of z dz. So let us suppose that is equation number 1 and that is the equation number 2. So you can see we can cancel out the 2, take the 1 by 2 as a common, we can cancel out, and we can write here over the curve C, that is mod of z is equal to r cos of 3z dz over 1 plus z square multiplied to 4 plus z square is equal to negative r to r f of x dx plus line into other curve C having a radius r f of z dz. So now further we will calculate this integral by using the Cauchy residue theorem. So by using first of all we need to find the singularity. So first of all we need to put the denominator 1 plus z square and 4 plus z square is equal to 0. Then we will get a value of z, that is positive negative I and positive negative 2i. So out of this only z is equal to I and 2i belong to the half circle, upper half circle, mod of z is equal to r. So we can say value of z, that is I and 2i r. simple poles. If the simple pole, then the value of the integral over the curve C mod of z is equal to r cos of 3z dz upon 1 plus z square and 4 plus z square can be written as we know that e to the power of 3iz is equal to cos 3z plus I sin 3z. Mean cos of 3z is a real part of e to the power of I 3z. So we can write the real part of over the curve C, that is mod of z is equal to r e to the power of 3iz dz over 1 plus z square multiplied to 4 plus z square. So now here, so from here as we can see that actually the z is equal to I and 2I are the simple pole. So by using Cauchy residue theorem, the value of this integral can be calculated as over the curve C mod of z is equal to r e to the power of 3iz dz over 1 plus z square and 4 plus z square is equal to 2 pi I, the sum of residue at z is equal to I plus sum of residue at z is equal to 2I. So by using that, so we can write that is equation number 3. So that is equation number 3. So by using that, we can write here 2 pi I limit z tending to I, z negative I e to the power of 3iz over 1 plus z square and 4 plus z square plus limit z tending to I, z negative 2I e to the power of 3iz over 1 plus z square 4 plus z square. So now further you can see we can simplify, after simplifying we can find the limit here, limit z tending to I, that is z negative I e to the power of 3iz over z plus I, z negative I, z square plus 4 plus limit z tending to, here below that is a 2I, sorry, that is a 2I. So now further we can write z negative 2I e to the power of 3iz over 1 plus z square z plus 2I z negative 2I. So now here this factor get cancel out, this is get cancel out, and I put after substituting the limit here it will give negative 3 over 2I and I square, that is a 4 negative 1 plus e to the power of negative 6 over, that is 1 negative 4 multiplied to 4I. So now further simplifying, this one is equal to 2 pi I multiplied to e to the power of negative 3 over 6I negative e to the power of negative 6 over 12 times of I. You can see this I, take the I as a common and cancel out here. So we will get uh, that is 2 pi multiply to e to the power of negative 3 over 6 negative e to the power of negative 6 over 12. So multiply the whole bracket by 2, it will give pi times of e to the power of negative 3 over 3 negative e to the power of negative 6 over 12. So finally we can write the value of the integral over the curve C, that is mod of z is equal to r cos of 3 times of z dz upon 1 plus z square and 4 plus z square is equal to the real part of the value of the integral will be the pi times of e to the power of negative 3 over 3 negative e to the power of negative 6 over 12. So finally this is the real value. So this value is equal to pi times of, sorry, that is a pi times of e to the power of negative 3 over 3 negative e to the power of negative 6 over 12. So this is our required value. So now further we need to find, now we need to find the value of the line integral over the curve C of r cos of 3 times of 3z dz over 1 plus z square and 4 plus z square. So now this can be written as the real part of the integral over the curve C of r e to the power of 3iz dz over 1 plus z square and 4 plus z square. So along the curve C, that is a half circle. So along the half circle we need to substitute, we need to put z is equal to r, because here the along the curve CR, that is the mod of z is equal to r. Center is 0, radius is r, so we can put z is equal to r e to the power of I theta, and dz is equal to ri e to the power of I theta d theta. Take the on modulus, mod of z is equal to r, and take the mod of z dz is equal to r d theta. So this value will be required, we will put this value in next integration. So further we need to take the mod, we need to take the modulus over the curve C, because this is a complex, this integral is nothing that is a complex value integral. So this integral has we need to convert this integral into real integral. So we need to take the modulus of over the whole integral, that is, we can say that is e to the power of 3iz dz over 1 plus z square and 4 plus z square. So after taking the mod, take the modulus under the integral over the curve C with this having radius r, mod of e to the power of 3iz dz over 1 plus z square and 4 plus z square. So further we can write here, that is over the curve C of r mod of e to the power of 3iz over 1 plus z square and 4 plus z square and mod of dz. So this can be written as, put the value of, put the value of r here, that is e to the power of 3i r e to the power of I theta, this will be equal to, that is r square negative 1 r square negative 4, and mod of dz will be, that is r d theta. And this limit of integration will be, theta will vary from 0 to pi. So here will be, simplify this here, e to the power of 3 times of I r, we can write here cos theta plus I sin theta. So we need to take the modulus here. So that is r square negative 1 r square negative 4 r d theta. So now we need to write the modulus here, 0 to pi. So we can write above e to the power of negative 3r sin theta dot e to the power of r 3i, sorry, 3ri cos theta r d theta over r square negative 1 and r square negative 4. Take the modulus here. After simplifying, as we can see that this modulus value will, that is 1. So we can write 0 to pi, that is a real value function, that is e to the power of negative 3r sin theta multiply to r d theta over r square negative 1 and r square negative 4. So now take the all the function of r, take outside the integral, because we are integrating the whole term with respect to theta. R square negative 4, that is 0 to pi e to the power of negative 3r sin theta d theta. So as we can see that r is positive quantity and sin theta also positive quantity for all theta belongs to 0 to pi. So we can say the r times of sin theta is positive quantity for all theta belongs to 0 to pi. So value of this integral will be bounded. So we can write here r upon r square negative 1 r square negative 4, because it is very tedious process to find this value of the integral, but we know that this function is positive. So we can write here e to the power of negative 3 times of r sin theta will be bounded, will be bounded. Function is continuous, bounded, then value of the integral over the bounded region will be bounded. So we can write here, that is a multiple of this value will be less than m. So that is, so we can write here, that is value of integral 0 to pi e to the power of negative 3r sin theta d theta is less than equal to m. So therefore the value will be the r times of m over r square negative 1 r square negative 4. So therefore we can say, as r tending to infinity, the rational value rm upon r square negative 1 r square negative 4 tending to 0. So therefore The value of the integral over the curve CR, that is e to the power of 3iz dz, that is 1 plus z square and 4 plus z square will be tending to 0. If this value of integral tending to 0, then value of this integral over the curve C having radius r cos of 3 dz over 1 plus z square 4 plus z square tending to 0. So therefore the value of the integral over the curve C cos of 3 days 3 z dz over 1 plus z square 4 plus z square is equal to over the integral negative r to r f of x dx plus over the curve C of r cos of 3 dz over 1 plus z square 4 plus z square. So now as r tending to infinity, value of this integral will be, that is a pi times of e to the power of negative 3 over 3 negative e to the power of negative 6 over 6. This will be negative infinity to infinity f of x, that is a cos of 3x dx over 1 plus x square and 4 plus x square, and this value will be 0. So now it implies the pi times of e to the power of negative 3 over 3 negative e to the power of negative 6 over 6 is equal to the 2 times of 0 to infinity cos of 3x dx over 1 plus x square and 4 plus x square. So finally we can write here, that is the value of the integral 0 to infinity cos of 3x dx over 1 plus x square and 4 plus x square is equal to pi by 2 in bracket e to the power of negative 3 over 3 negative e to the power of negative 6 over 6, and this is our required final answer. So now in this problem, so let us consider the given integral, that is I 0 to infinity x to the power 3 sin x dx over a square plus x square and b square plus x square. So as you can see, the function f of x cube sin x and a square plus x square and b square plus x square is even function. So if this even function, then we can write this integral, that is 1 by 2 negative infinity to positive infinity x to the power of 3 sin x dx over a square plus x square and b square plus x square. So now we need to replace the x by z, then this will be 1 by 2 negative infinity. So this integral will be changed over the curve C, z to the power 3 sin of z dz over a square plus z square and b square plus z square, and this integral will be equal to, also we know that sin z is the real sorry, sin z is equal to imaginary part of e to the power of iz. So now we can write here that is a imaginary part of 1 by 2 over the curve c z to the power 3 e to the power of iz dz over a square plus z square and b square plus z square. So now finally here that is will be that is a imaginary. So now we can solve, we will solve this integral by using Cauchy residue theorem. So now let us draw the diagram. That is the upper half circle. The center will be that is a 0. Radius vary from negative r to r, and the direction will be counterclockwise, that is anti-clockwise direction. So therefore by using that, so we can write the over the curve c f of z dz is equal to negative r to r. This whole integral over the curve c, the sum of the integration over the real axis f of x dx plus over the curve c with having radius r f of z dz. So putting this value over the curve c, that is imaginary part of 1 by 2 z to the power of 3 e to the power of I times of z dz a square plus z square and b square plus z square. This will is equal to negative infinity r to r, take 1 by 2, divide the whole integration 1 by 2. We can write here x to the power of 3 sin x dx over a square plus x square and b square plus x square plus over the curve c having a radius r, divide by 2, and we can write here z to the power 3 sin z dz over a square plus z square and b square plus z square. So let us suppose that is equation number 1. So we can cancel out, take the common 1 by 2 and cancel out, and this can be written as the imaginary part of over the curve c z to the power 3 e to the power of iz dz over a square plus z square and b square plus z square, that is negative r to r x to the power of 3 sin x dx over a square plus x square b square plus x square plus the line complex integration over the curve c having radius r z to the power of 3 sin z dz over a square plus z square and b square plus z square. So let us suppose that is equation number 2. Now we will solve this integral left hand side by using the Cauchy residue theorem. So first of all we need to put the denominator a square plus z square and b square plus z square is equal to 0. So from here we will get value of z positive negative ai positive negative bi. So only ai and bi will belong to the upper half circle. Upper half circle. So we can say that z is equal to ai and bi are simple poles. So therefore, by using so the imaginary part of the integral over the curve C, f of z dz will be equal to 2 pi I sum of the residue at z is equal to ai plus residue at z is equal to bi. So this will is equal to 2 pi I multiply to the limit z tending to ai, z negative ai. So we can write here z to the power of 3 e to the power of iz, z to the power 3 e to the power iz upon a square plus z square b square plus z square and plus the limit z tending to bi, z negative bi, z to the power 3 e to the power of iz over a square plus z square b square plus z square. So now close the bracket and further simplifying, this is equal to 2 pi I, the limit z tending to ai, z negative ai e to the power of iz multiplied to the power 3 over z plus ai, z negative ai, b square plus z square plus the limit z tending to bi, z negative bi, z to the power 3 iz over a square plus z square, and here will be z plus bi, z negative bi. So now cancel this factor here and further simplifying, this value is equal to 2 pi I multiply to the limit. Apply the limit here directly. We can write here ai to the whole power 3 e to the power of I multiply to y. It will give negative a over 2ai. It will give b square negative a square plus bi to the whole power 3 e to the power of negative b over 2b, sorry, so further it will give, that is 2bi, and here will be, that is a square negative b square. So now further simplifying, it will give, that is 2 pi I multiply to negative a to the power 3 multiply to I multiplied e to the power of negative a over 2 ai multiply to b square negative a square negative b to the power 3 multiplied to I multiplied e to the power of negative b over 2bi multiplied to a square negative b square. So you can see I to I get cancel out. 1a will be cancel out. It will give 2. I to I get cancel out. 1b cancel. It will give 2 here. So we can write 2 pi I. That is, take the negative sign common from this factor, or negative negative will be cancelled out, and it will give a square e to the power of negative a over 2 times of a square negative b square negative b square e to the power of negative b over 2 times of a square negative b square. So now take this factor common. It will give 2 pi I over 2 times of a square negative b square, that is a square e to the power of negative a negative b square e to the power of negative b. 2 to 2 get cancel out. So this, so now the imaginary part of the integral over the curve C, z to the power of 3 e to the power of iz dz upon a square plus z square b square plus z square will be equal to pi upon a square negative b square, bracket will be a square e to the power of negative a negative b square e to the power of negative b. So this is our required value. So now further we can write directly the value of the integral over the curve C having radius r, z to the power 3 sin z dz over, that is a square plus z square b square plus z square will give tending to 0 as r tending to infinity when we will when the value of when we'll put the value of z is equal to r e to the power of I theta. So therefore we can write the value of the integral over the curve C f of z dz is equal to negative r to r f of x dx plus value of the integral over the curve C having a radius r f of z dz. So now as r tending to infinity, this value will be is equal to pi upon a square negative b square in bracket a square e to the power of negative a negative b square e to the power of negative b, and as r tending to infinity this value is equal to negative infinity to infinity f of x dx, and this limit will be 0. So finally we can write here, so now pi upon a square negative b square a square e to the power of negative a negative b square e to the power of negative b is equal to 2 times of 0 to infinity f of x dx. So therefore the value of integral 0 to infinity f of x dx is equal to pi over 2 times of a square negative b square a square e to the power of negative a negative b square e to the power of negative b. So finally we can write the value of the integral 0 to infinity x to the power 3 sin x dx over a square plus x square b square plus x square is equal to pi upon 2 a square negative b square in bracket e to the power of a square e to the power negative a negative b square e to the power negative b, and this is our required final answer. In this integral, as we know that we need to replace x by z, then integral will be negative infinity to infinity cos of x dx over a square plus x square b square plus x square will be equal to over the curve c cos of z dz over a square plus z square and b square plus z square. So now for solving this integral, we need to draw the diagram. So this is our real x-axis, which this is upper half circle. So that is our y-axis, and this is our x-axis, and that is the curve is along the anti-clockwise direction. Center is 0 and radius vary from negative r to r. So this is a curve having radius r. So the curve C will be that is the mod of z is equal to r. So now further this whole integration over the curve C that is mod of z r will be equal to cos of z dz over a square plus z square b square plus z square will be equal to the sum of the integral over the real axis negative r to r f of x dx plus over the curve having radius r f of z dz. So that is, let us suppose the equation number 1. So now here first of all we will solve this integral. So now the value of this integral over the curve mod of z is equal to r cos of z dz over a square plus z square and b square plus z square will be equal to the real part of the integral over the curve c e to the power of iz dz over a square plus z square b square plus z square. So now further solving, first of all we need to find the singularity. So we need to put a square plus z square b square plus z square is equal to 0. It implies value of z is equal to positive negative ai positive negative bi. It implies value of z is equal to only ai and bi belong to the upper half circle mod of z is equal to r. So we can say that value of z is equal to ai and bi are simple poles. If there is simple poles, we can find the value of the integral over the curve c cos of z dz over a square plus z square b square plus z square will be equal to the real part of. So this integral will be calculated by using the Cauchy residue theorem. So that is real part of 2 pi I sum of the residue at z is equal to ai plus residue at z is equal to bi. So now this value will be equal to the real part of 2 pi I, that is a limit z tending to ai z negative ai e to the power of iz over z square plus a square and z square plus b square plus limit z tending to bi z negative bi e to the power of iz over a square plus z square and b square plus z square. So this value is equal to this is a real part of 2 pi I limit z tending to ai. It will give z negative ai e to the power of iz over z plus ai z negative ai z square plus b square plus limit z tending to bi z negative bi e to the power of iz over a square plus z square z negative bi and z plus bi. So here we can say this factor get cancel out here. So further we can write that is the real part of integral 2 pi I. It will give, put the substitute the limit here, that is e to the power of negative a over 2 times of ai b square negative a square e to the power of negative b over 2 times of bi, and it will give a square negative b square. So as we can see that if I will take the common 2i, so this 2i and 2i will be cancel this value here. So after the, now this is equal to the real part of take b square negative a as a common. So from here it will give pi upon b square negative a square. So in bracket e to the power negative a upon a negative e to the power of negative b upon b. So in the standard form this can be written as, that is the real part of pi upon b square negative a square e to the power of negative b upon b negative e to the power of negative a upon a. So now further, so now it implies the value of the integral over the curve c cos of z dz over a square plus z square b square plus z square is equal to pi upon b square negative a square multiplied to e to the power of negative b upon b negative e to the power of negative a upon a. And further, the value of the integral over the c having a radius r, that is cos of z dz over a square plus z square and b square plus z square tending to 0 as r tending to infinity when value of z is equal to r e to the power of I theta. So further we can write that is the value of the integral over the curve c cos of z dz over a square plus z square b square plus z square is equal to negative r to r f of x dx plus over the curve c having radius r f of z dz. So now as r tending to infinity, this value is going to be pi upon b square negative a square in bracket e to the power of negative b upon b e to the power of negative a upon a, that is negative infinity to infinity f of x dx. So therefore our required final answer, negative infinity to infinity cos of x dx upon a square plus x square b square plus x square is equal to pi upon b square negative a square multiplied to e to the power of negative b upon b negative e to the power of negative a upon a, and this is our required final answer.